So we're going to continue with Chapter 8, looking at solving systems of inequalities. We have been working on solving all kinds of different systems of equations, all right, 2-variable, 3-variable systems. Now we're shifting to the inequality ones. All right, our method for solving these typically is graphing. Okay, so we're going to look at how do we graph linear inequalities just in 2 variables. Okay, go back a step. Then we're going to look at graphing nonlinear inequalities in 2 variables. And then tomorrow we'll start putting it together as a system. Okay, so first step. You are going to sketch the graph of the equation. In other words, don't worry about whether it's less than or greater than. Just pretend there's an equal sign in there. All right, and look at how you would graph that. Then we do look at the inequality to help us determine if it should be a solid or dotted line. Do you remember when we used the solid lines? If it's equal to. So we can use solid lines for less than or equal or greater than or equal. But if there's no equal sign, strictly less than or greater than, then we have to make it dotted. Okay? What that's going to do, picture taking a coordinate plane and drawing a line through it. Okay? What we've done is we've created 2 what we call half planes. We've broken that coordinate graph into 2 parts. And what we have to do is figure out which part is the one we want. All right? To do that, we are going to test a point. An easy point to use is the origin. The only restriction is we cannot use the origin if our line goes through it. So if your line or curve is going through the origin, you're going to have to pick a different point to try. Okay? In each half plane, either all of the points are solutions or none of them are, which means if I tested a point here and I said it worked, then it means all the points up here would work. If I tested a point up here and it didn't work, then I'd want to shade everything down here. Does that make sense? It's an all or nothing idea. Okay, so let's go through and look at what these shapes should be. The first one, we are graphing x is greater than 2. Picture x equaling 2 instead. What would that look like? X equaling 2. What kind of line is it? It is going to be solid or dotted. It would be dotted because it's not equal to. But if we were picturing x equals 2, right? What type of line is it? What do we call lines that are straight up and down? Vertical. It's a vertical line, right? X equaling 2 is a vertical line. Since we want it to be greater than 2, we are going to make it dotted. We're going to put arrows on the ends. All lines continue, both directions. And now when we have just a single variable like this, we can still do the testing a point idea, but it should be fairly obvious which side we want to shade. Okay, but let's say we are testing a point. We put 0 in for x. In other words, I'm checking that point right there. Does it make a true statement? Is 0 bigger than 2? No. So I don't want that point. That means the points to the left of my dotted line aren't working. I'm going to shade this side. Okay? And again, when there's just a single variable like this, could you have said which side of that line has x values that are bigger than 2? They'd be on the right side. Okay? Our second equation, or inequality, y is less than -4. Will it be solid or dotted? Dotted again. Is it going to be a vertical line again? No, this time it is horizontal. Horizontal line at -4. We said it was going to be dotted. And then we want values for y that are smaller than -4. So is that above or below it? It's below. Okay? And again, if we tested a point, we put 0 in for y, it makes a false statement. 0 is not smaller than -4. So we don't want the origin, we want the other side. All right. Example 3 has two variables now. So we aren't looking at vertical and horizontal lines, we're looking at the slanted lines, sometimes referred to as oblique lines. Okay? Picture y equals mx plus b. Is it in that same format? So where would we start this graph? At 2. 2 is your y-intercept. So we're going to cross the y-axis at 2. And what does the 3 tell us? That's the slope. So we are going to rise 3 and run 1. We can also go down 3 and back 1 if we need more points. Okay? Solid or dotted? This time it is a solid line. Does the line go through the origin? No. So we should be able to use the origin as our test point. Okay? So I'm going to put in 0, 0 for the origin. And look at the statement that we have left. We have 0 has to be greater than or equal to 2. Is 0 greater than or equal to 2? So I don't want the origin. I would shade that side. All right. The last couple are non-linear. So talk at your tables quickly. What shape would this next one be? What shape? I'm hearing parabola. Agree, disagree? So we could make a t-chart to graph a parabola, but if you can think in terms of those transformations, what have we done to a basic y equals x squared graph? Where did we move it? The -9 here moved it down 9. Okay, so a basic parabola, just y equals x squared, has those 5 points, right? 0, 0, 1, 1, 2, 4, and then their mirror image. Can we move those all down 9? All right, so shifting down 9, our vertex is going to be there. My 1, 1 point moves down to here. The 2, 4 moves down to here. And then we have the mirror image. Okay. Will this be a solid or dotted parabola? Solid. Okay, so we're going to draw that in. It actually has x-intercepts at 3 and -3. If you plug those in, your equation, your y value comes out 0. Okay, so we have a good picture of our parabola. We now have to figure out, are we shading inside or outside of that parabola? Okay, so if I test the origin, which is inside the parabola, does it make a true statement? 0 is greater than or equal to -9. So all the points inside the parabola are going to work, and I would shade all of that. Okay. Talk at your tables briefly. What kind of transformations have we done on this next one? I heard it's flipped. It's reflected over the x-axis. So we have an upside down parabola. What else have we done? Up 4. Okay, so we have an upside down parabola that's been shifted up 4. Okay, so again, I'm going to start with my original parent function points. Flip it upside down and move it up 4. So the vertex, if I flip it upside down, it's still at 0, 0. Moving it up 4 gives me a vertex there. Okay. The point 1, 1, if I flip it upside down, reflected over x, it's there. And I move it up 4, it's here. Okay. The point 2, 4, when I flip it over the x-axis, is down there. Moving it up 4 puts it there. Okay, I'm going to reflect those over and get the other side of this parabola. Solid or dotted? Solid. All right. Then we have to test a point. Can we use the origin again? All right. Negative 0 squared is just 0. Is 0 greater than or equal to 4? No, which means the origin doesn't work now. I don't want the points inside the parabola. I need everything on the outside. Okay? All right. Our last two are not parabolas. Anybody know what they are? We talked a little bit about it last semester. They are circles. Okay? We are going to spend some time later this semester looking at different conic sections. Circles is one of those. But our basic equation for a circle is x squared plus y squared equals r squared, the radius squared. Okay? In this format, our center is the origin, and our radius will be the square root of whatever r squared is. Okay? So looking at our first example, we have x squared plus y squared is greater than or equal to 36. That is a circle centered at the origin, and it has a radius of what? Radius would be 6. So we're going to put a dot at the origin, and then we're going to go out in all 4 directions, okay? 6 spaces. Should I make that circle solid or dotted? Solid, okay. And then, can we test the origin? Origin is not on the outside edge of my circle, so I can use the origin. Does it work? If I put zeros in there, is 0 greater than 36? No. So I don't want the origin. It means I don't want the stuff inside the circle. I want it to be outside. Okay? And if you think about it, we want the radius squared to be bigger than 36, right? So we want all the points that would be bigger than 6 spaces from the origin. That would be the things on the outside of that circle. All right, our last one is still a circle, but this time it's been shifted. So instead of being centered at 0, 0, our center is going to be HK. And if we think in terms of those transformations that we've done in the past, our H value is going to move things left, right, and our K value moved things up and down. Okay? We still have a radius of R. All right, so based on this equation, x minus 1 squared, which way did we move it? Right 1? So we went right 1. Y minus 4, we moved which way? Y minus K, what's the K value? K is 4, H is 1, yes? So we went right 1 and up 4. Another way to look at it is what makes each of those parentheses 0. Okay, so x minus 1 is 0 when x is 1. Y minus 4 is 0 when y is 4. That's my new center. Okay, so 1, 4. I'm going to put a dot there. What's my radius? Radius squared is 16, so radius would be 4. So from that new center point, can I go out 4 in each direction? Okay, so I'm going to just count 4 spaces. Will this be solid or dotted circle? This one should be dotted. All right, now, does it go through the origin? I know it touches the x-axis at 1, 0. And because it's a circle, it's going to curve up from there. Okay, so even though it kind of looks when I drew the dotted line that it went through the origin, it's not going through the origin. So technically, I could still use the origin as a test point. But I'm going to show you how to use a different point, just so you have that idea. Let's say we pick the point 1, 1. Okay? So I'm picking a point inside my circle to see if it works. Put a 1 in. 1 minus 1 is 0, so that part drops out. 1 minus 4 is -3. Squared would be 9. Is 9 smaller than 16? So that point works, which means all the points inside the circle are going to work. Okay? All right, so I will get you guys some graph paper. Your homework is on page 847. You're going to do 1 through 21 odd.